Okay, so up to now we were discussing, okay, this is one example of a polarizer. You are probably familiar with these things. When you go to a cinema, this is where you use it. To create this three-dimensional image, the way we perceive three-dimensional image is that both of our eyes see different things. And so the brain, each eye sees a two-dimensional image, but the brain kind of interprets it as a three-dimensional structure. So in movies, so you just put these glasses on. Basically, these are two different kinds of polarizers. And on the screen, two images are superimposed, each one having one polarization, so that each eye, these two polarizers are different, so each eye sees a different image. So although when you remove this, you see all this color confusion on the screen. When you put this on, since each of your eyes sees just one of the images, and so they create this three-dimensional structure. Now, another use of these polarizers, or the polarization of light, is in photography. I have some images. Now, this we will study probably next week. I don't think we will be able to cover it today. This is an image of a lake. So you see there are these fishes, but there is a lot of reflection through the surface. This is the same image taken using a polarizer. The difference between this one and this one is that in this second image, there are no reflections, or the reflections are kind of minimal. They are minimized. And as we will see, the reflected image is usually polarized. So by using a suitable polarizer, you can just eliminate most of the reflected image. What remains is the image of what lies behind that. This is just another use of the polarization of light. Now let's come to electromagnetic waves. We have been discussing electromagnetic waves this week, and we basically saw that it's possible that we might have these electromagnetic waves in vacuum and also in medium. And in general, in medium, what we had shown that in the absence of any charges, let's say we have a wave moving in this direction. This is the wave vector. If the electric field points in this direction, electric field has to be perpendicular to the wave vector. The magnetic field will be in this direction. It also has to be perpendicular to the wave vector and also to the electric field. So these three vectors form an orthonormal coordinate system, basically. And their magnitudes are related. The magnitude of E0 is just V times B0. Well, I'm not putting C over here. V is the velocity of this electromagnetic wave in medium. If the medium is vacuum, then V is equal to C. So V is basically C over N. N being the refractive index, and N, if you remember, we had derived N was equal to which one is 0? Check it. Well, you see, if you remember the wave equation, we have the second time derivative. This should be 1 over c squared in vacuum. Or this is epsilon 0, mu 0. This is in vacuum. This is what tells us what the speed is, the coefficient over here. In medium, this is epsilon mu. So V squared, V is basically 1 over square root of epsilon mu. This is equal to 1 over square root of epsilon 0, mu 0, square root of epsilon 0, mu 0, divided by epsilon mu. This is C. This is 1 over N. So it is epsilon 0, mu 0 down there. Well, n should be a number larger than 1, because the speed of anything in medium or not should be always less than or equal to c. So n should be larger than 1, and epsilon is larger than epsilon 0. Mu is most of the time almost mu 0. The deviation of mu for most materials from mu 0 is smaller than 10 to the power minus 4. So for most materials, we can just ignore it. And the last thing we wanted to discuss was, okay, so this is what happens in a homogeneous medium. What if the medium is not homogeneous? A typical example is glass. So the light just passes through glass. So what happens then? Another example that you are probably, I'm sure you have seen, when you are especially traveling on a hot day on the road, if you just look ahead in the road, you will see as if there is water there. Well, basically, that's not water, that's just a reflection of the sky. From where? Well, the road does not reflect the light. So it doesn't come from the reflection. But the thing is, if this is the road, this is your car, well, there are some light rays that start from the sky. Well, the atmosphere is not homogeneous, especially when there is a large temperature gradient. The density changes a lot. I mean, if you heat gas at the same pressure, its density is reduced. So the temperature will be changed, the density will be changing, and the change in the density will cause a change in this N refractive index. So basically, this is another example of an inhomogeneous medium. Well, this will be kind of more complicated for us. We will just look at the basic case of the mirror, because they're just basically two different index of refraction. So in that sense, it is easier. But once we study that, you can also apply it to here by just assuming the atmosphere as layers of medium with homogeneous refractive index. And the refractive index gets smaller and smaller as you approach the road. And so the light will travel such a path. Well, it's not just bending over here, it just follows a smooth path. So you, from here, will observe this light, although it's coming from the sky, as if it's coming from there. And then your brain interprets it as a kind of a mirror. So this is how this mirage forms. Now, why does it bend up? We will see it. Now, let's say this reflection first. So what we will assume is, any questions up to this point, by the way? Any of the things that we had covered? So here we have the relation between E and B, the magnitudes, and this K vector and the frequency are related by omega over K, let's say, or omega over K, this is equal to V. Any questions up to here? Now let's look at this problem, reflection and transmission. So we have these two different media with dielectric constant, electric and magnetic permeabilities, and the other medium, mu2, we send some light, some electromagnetic wave from this medium. Let's call it E1. This is K1. This is E2. No, this is B1. Well, some of it will just pass through. So here we have K2, E2, B2. And some of it will be just reflect back. K1 prime, E1 prime. What's the direction of E1 prime? If this is the direction of E1 prime? Into the screen. And let's say that E1 is let's choose our coordinate axis. This is X, Y, and Z. E1 is some number in the X direction. B1 is some number in the Y direction. So these are, we will assume them to be positive. Those are basically the wave we sent. I'm choosing the X direction to be in the direction of the E1, and the Y direction is the direction of B1. So that's why these numbers are positive. E1 prime will be some number in the X direction. B1 prime will be minus some number. Now, in fact, even these numbers we can just put. B1 is E1 over V. We know the magnitude. This is E1 prime over V, V1 in the Y direction. Well, I don't know whether E1 prime is positive or negative. That we will drive eventually. But what I definitely know is that these two signs are different. So I'm not really assuming that E1 prime is pointing upward. So if this number turns out to be negative, E1 prime will be pointing downward. And finally, for the transmitted wave, E2 is some number in the X direction. B2 is E2 over V2 in the Y direction. Again, I don't know whether E2 is positive or negative, so the transmitted electric field might be pointing in the same direction as the incident electric field, or it might be pointing in the opposite direction. Also keep in mind that although I'm not writing them explicitly, all of these waves have the overall factor. On the left-hand side, we have e to the power I k1 z minus omega t. On the right-hand side, we have e to the power minus I, now plus I, k2z minus omega t. Sorry. Now K1 is some magnitude in the Z direction. K1 prime is the same magnitude in the minus Z direction. So plus sign is for the incoming wave, minus sign for the reflected wave. Here, well, there's just a single sign for the transmitted wave. Just these factors are there. Now, we have these unknowns now. We don't know what E1 prime is. We don't know what E2 is. So since we are preparing the wave, I'm assuming that we already know E1. That is something we decide when we are sending our wave. So to determine these two unknowns, we need two conditions. And those two conditions, they just come from the Maxwell's equations. So let's look at the Maxwell's equations in the absence of any free charges. So we know that the Maxwell's equations are divergence of D in the absence of any free charges is 0. Divergence of B, 0. Curl of E, minus del B by del T, and curl of B no, sorry, curl of H
J plus.
there are no free charges. They're not moving around. And furthermore, H is equal to B over mu. And D is equal to epsilon E. So these are the relations we have. Now let's look at what they mean. You see, I will be looking at how the D, E, B, H fields change as I go from one side of my surface to the other side of my surface. So here basically that's what I have. I have a surface and the electric field. I need to relate the electric field on the left of this surface to the electric field on the right of this surface. Now this first equation basically tells me that the perpendicular component of the displacement field, perpendicular to the surface, its change as you go from one side of the surface to the other side of the surface is 0. Or the change in epsilon times E. Of course, the perpendicular component of E is 0. Well, to start with, since we know that the epsilon is changing from the left to the right, if E perpendicular is non-zero, then it should be discontinuous. So that the change in epsilon perp as we go from one side of the surface to the other side of the surface should compensate the change in epsilon. Well, in our problem, the electric field, what is the perpendicular component of these electric fields? Perpendicular to the surface. 0. So E perp is 0. It is 0 on the left, it is 0 on the right. D perp is 0 on the left, 0 on the right. So automatically this equation is satisfied. That is, in this case, this boundary condition doesn't really tell me anything. Let's look at the second condition. Well, this condition, just like the previous condition, tells me that the perpendicular component of B, its change as we cross from one side of the surface to the other side is 0. But again, in this problem, the perpendicular component of B is 0 to start with. So this also doesn't tell us anything. Now let's come to these equations. Curl of E is equal to minus the derivative of B by T. Well, this tells me that the change in the parallel component of the electric field is 0. So the parallel component of the electric field, the parallel to the surface, it should be the same on both sides of the surface. If you remember the derivation just starts by assuming a rectangular loop such that one side of this loop is in one medium, the other on one side of the surface, the other side of the loop is on the other side of the surface. And this equation basically tells me that the integral of the electric field around that loop should be equal to the rate of change of the magnetic flux. But as we set the width of this loop to 0, the flux goes to 0, so its change goes to 0. So the integral of the electric field around the very thin loop, which goes over both sides of my surface, should be 0. So that tells me that the parallel component of the electric field should be the same, because as you go around the loop, they should just cancel each other. And similarly, this equation tells me that the change in the parallel component of the H field should be 0. But this tells me that the change in the parallel component of B over mu should be 0. So if mu changes from one side of the surface to the other side of the surface, the parallel component of B, it should either be 0 or it should also change discontinuously. Well, there is one reason why I am putting these vector signs over here. They are on purpose, because the perpendicular direction is a single direction. So it's just one component. So I can talk about that component or the component or the vector in that direction. They are basically the same thing. But the parallel component, the parallel to the surface, is a vector. It can be pointing in this direction, in that direction, in that direction. That's why I'm putting this vector sign. Now, of course, we need to apply these conditions these boundary conditions should be valid in every case, as long as we don't have any surface charges or surface currents running over our surface. Not just in our case, but they should be satisfied in all cases. Now, in our special case, we said that the first two equations do not tell us anything new, basically because the perpendicular component of the electric and the magnetic fields, they are automatically zero, so those conditions are automatically satisfied. Now let's look at the electric field. Now the electric field on the left-hand side. So electric field, let me use this sign. So I will just assume that this is Z is equal to 0 plane. I will just choose my origin somewhere on that plane, on the interface. So this less than sign basically implies the electric field for points at Z less than 0. This should be equal to E1 in the x-hat direction, e to the power I k1z minus omega t, plus E1 prime in the x-hat direction, e to the power I minus k1z minus omega t. The electric field on the right-hand side, I only have the transmitted one, so this is E2 in the x-hat direction, e to the power I k2z minus omega t. So these are my conditions. Well, what did we just derive about well, these are, okay, to start with, these are both parallel to my electric field. So there is no perpendicular component, both are parallel. And we know that the parallel component of the electric field has to be continuous. So that condition tells me that E1 e to the power I k1, well, I'm calculating it at z is equal to 0. So k1z is automatically 0 minus I omega t plus E1 prime e to the power minus I omega t. This should be equal to E2 times e to the power minus I omega t. Well, to start with, I had already assumed that omega was the same on the left-hand side, on the right-hand side. That was basically an assumption. But you see, you can also show that they have to be the same. They have to have the same angular frequency, because if the frequencies are different on the left-hand side and on the right-hand side, or if they are different for the incident and the reflected wave, this relation you can satisfy at a particular time, maybe, but you cannot satisfy it at all times. If you want to satisfy this condition at all times, the frequencies of each one of these waves have to be identical, so that we can just cancel the time dependence, and if the remaining time independent equation is satisfied, then this condition is satisfied at all times. So let's just cancel them. So E1 should be equal to E2 minus E1 prime. So you see, we have two unknowns. To determine these two unknowns, we need two equations in terms of those two unknowns. These are my two unknowns. This is one of my equations for these two unknowns in terms of the quantities that I already know. E1 is something I know, so that's why I keep E1 on one side and the unknowns on the other side. The kz. Why don't we have this kz? Because we are looking on this plane. Z is equal to 0 plane. On the left of that z is equal to 0 plane, it should be equal, the electric field on the left of z is equal to 0 plane should be equal to the electric field on the right of z is equal to 0 plane. So they are both z is equal to 0. So these K2z, K1z, they are 0.
Hocam bu angular frekansının tüm dalgalar için aynı olduğunu su dalgası deneyinde görebilir miyiz peki?
You see, I'm not saying that omega is the same for all waves. What I'm saying here is that if you send an electromagnetic wave in such a in the interface between two mediums, the wave you send has a certain angular frequency. If it has a certain angular frequency, the reflected wave and the transmitted wave should have all the same frequency. You can do this experiment also with water waves. In water waves, what you should do is just take a cup, put some brick on one side, so that you will make the depth different. If the depths are different, just create some wave, send it through this, the part where the depth is different. You will see that some wave is reflected, some wave is transmitted, but all have the same frequency. The frequency of all of them is equal to the frequency of the incident wave. But of course, the incident wave can have any frequency that you create. Just similarly here, the incident electromagnetic wave can have any frequency. There is no limitation on that. But once you send a wave with a definite frequency, the reflected and the transmitted waves have the same frequency.
Bunların değişme olasılığı yok mu?
No. Well, they can, if they differ, you cannot satisfy this condition at all times. Now let's look at our other condition. The parallel component of B over mu should be the same on the left-hand side and also on the right-hand side. That's our other condition. So let's see, what is the B field on the left-hand side and on the right-hand side? On the left-hand side, the B field is E1 over V1 in the y-hat direction, e to power I, K1z is again 0, minus I omega t, plus or minus E1 prime over V1 in the y-hat e to power minus I omega t. This should be equal, this is the magnetic field right on the left-hand side. Well, let me add this. And the magnetic field on the right-hand side of this surface is given by E2 over V2 in the y-hat direction e to power I K2z minus omega t. And my boundary condition tells me that the magnetic field on the left-hand side evaluated at z is equal to 0 divided by mu1. This should be equal to the magnetic field on the right-hand side of my surface, again evaluated on the surface, divided by mu2. Well, I'm equating the magnetic fields because my boundary condition tells me that the parallel component of the magnetic fields over mu should be continuous, but our magnetic field only has the parallel component, doesn't have the perpendicular component.
Hocam bunu elektrik alanı için yazdın mı?
No, because we have these two boundary conditions. The first line, that is the boundary condition I have for the electric field, and the second line is the boundary condition I have for the B field. I already used my boundary condition in terms of, on the electric field, it is this one. It gave me one condition. And now I have the condition on the B field. That is my second boundary condition on the top of the screen. Now I just put in the B left and B right, so it just gives me E1 over V1. Well, Z is equal to 0, so these terms are already absent. Well, minus I omega t is e to the power minus I omega t, they are also common, so I will also straight away eliminate them. What I will be left with is E1 over V1 times mu1 minus E1 prime over V1 mu1. This should be equal to E2 over V2 mu2. Or let me rewrite this. E1 over V1 mu1 should be equal to E1 prime over V1 mu1 plus E2 over V2 mu2. These are the two relations relating the unknowns E1 prime and E2 to our known E1. And then what is left is we need to solve those two equations. Well, let's solve them. Let me just multiply the second equation by 1 over V1 mu1 and add them. Well, if I multiply the second equation by 1 over V1 mu1 and add them, these E1 prime terms, they will just cancel. So what I will end up having is twice E1 over V1 mu1. This should be equal to E2, 1 over V2 mu2 minus 1 over V1 mu1 plus so E2 should be equal to E1 times 2 over V1 mu1 times V1 mu1 V2 mu2 over V1 mu1 plus V2 mu2. Well, these cancels, so this is E2 is equal to twice V2 mu2 divided by V1 mu1 plus V2 mu2 times E1. So we know how much of it is transmitted. Well, let's calculate E1 prime. Well, you see E1 prime just from that equation over there. We can use that one. E1 prime is equal to E2 minus E1. We had already solved for E2. This is equal to twice V2 mu2 divided by V1 mu1 plus V2 mu2 minus 1 times E1. Or this is V2 mu2 minus V1 mu1 divided by V2 mu2 plus V1 mu1 times E1. This is our E1. Okay, first of all, about directions. You see, E2 is always has the same sign as E1. If E1 is positive, E2 is positive. So the transmitted electric field is always in the direction of the incident electric field. But the reflected electric field, it depends. You see, if in the second medium it is moving faster, if V2 is larger than V1, then we know that E1 prime is also positive. But if in the transmitted medium, it's moving slower, if V2 is smaller than V1, in that case, the reflected wave is reversed. Well, in fact, we didn't study that example in detail, but if you study the waves on a string, basically you observe the same phenomena. So if, for example, you send a wave to you start with a light string and send the wave towards a heavier string, the reflected wave will reverse its direction. Now, for most materials, mu is almost mu zero. I mean, as I said, the deviation of mu from mu zero is of the order of 10 to the power minus 4 typically. So for most materials, we can make the assumption that mu1 is approximately equal to mu2, which is approximately equal to mu zero. Well, in such a case, E2 is equal to twice V2 over V1 plus V2, E1. Well, V2 is nothing but the speed of light divided by the index of refraction of that medium, divided by C over N1 plus C over N2 times E1. Or this is equal to twice N1 over N1 plus N2 times E1. And similarly, you can just do the same treatment for E1 prime. This will be equal to N1 minus N2 divided by N1 plus N2 times E1. So it's basically the refractive indices of medium, which to a large extent determines how much of your incident wave is reflected, how much of it will be transmitted. Of course, this is only true under this assumption, which is quite a good assumption for most typical materials.
These are not for the rays coming perpendicular?
Coming perpendicular to the surface. Now, another important property for us will be the intensity of this wave. Now, the intensity is basically defined as the energy per unit area per unit time. Well, per unit perpendicular area, let's say. Yeah, it's basically the pointing vector. More like energy flow. So when you say that a light is too intense, too bright, you use the same thing. When you say too bright or too intense, what you actually mean is that there's too much energy coming from there. When you have a bright light, when you have this lateral surface, the intensity drops because in the perpendicular direction there is not much energy flow. Anyway, it is proportional to intensity. Now you can work out the overall coefficients. Well, the energy flow, the pointing vector, is proportional to the electric square, E squared, electric field squared. We had already studied the pointing vector. And let's say we define the reflection coefficient as basically the reflected intensity divided by the incident intensity. And this is equal to E1 prime squared divided by E1 squared, which is Let's just look at the simpler case of when we assume that all mu's are equal to mu 0. This is equal to n1 minus n2 squared divided by n1 plus n2 squared. So the intensity is proportional to epsilon times E squared. You remember energy density is of a wave is equal to epsilon E squared. So what's the Poynting vector? What was the Poynting vector of this field? Over or times? Over. 1 over mu. Since we are looking in medium. So in our case, the magnitude of S, let's just look at that one. This is equal to E times B over mu. E times E over V times mu. So this is 1 over mu V E squared. This is the intensity. One over V is just n over mu times C E squared. Now we are assuming that mu is the same everywhere. It's equal to mu 0. C is constant, so intensity is n times E, proportional to n times E squared. Here n1 divided by n1. The reflected intensity is E1 prime squared. The incident is E1 squared. So it is that one over there. Now the transmitted intensity, transmission coefficient, will be n2 times E2 squared divided by n1 times E1 squared, which will be, well, E2 is the second line at the top. So this is n2 over n1. E2 squared is 4 n1 squared divided by n1 plus n2 squared. E1 squares, they just cancel. So this is equal to 4 n1 n2 divided by n1 plus n2 squared. This is called the transmission coefficient. So basically it measures how much of you are sending some energy to your surface, how much of that energy is transmitted to the other side. And this is, R is called the reflection coefficient. This measures how much of the energy you send to your surface is reflected back. Well, if energy is conserved, all of the energy that you send is either transmitted or reflected. So the total probability of transmission and reflection should be equal to 1. Let's check that. Well, transmission was 4 n1 n2 divided by n1 plus n2 squared. Reflection was n1 minus n2 squared divided by n1 plus n2 squared. If you open up the parentheses, this will be n1 plus n2 squared divided by n1 plus n2 squared, which is 1. Well, kind of everything proceeds in a consistent manner, let's say. You see, in our derivation of these transmission and reflection coefficients, we didn't import energy conservation. We just import the condition that the parallel component or the perpendicular component, E or B or whatever our field should be continuous. And it turned out that energy is conserved. Well, we already know that energy should be conserved. And in fact, as one of our conditions, we could have just used this condition, the conservation of energy. Okay, any questions? Yeah, in the next hour, we will basically repeat the same things, but this time not for a wave that just goes perpendicular to the surface, but with an angle. What happens then? Okay, 10-minute break.